I've just hit the record button. Welcome back. Am I coming in loud and clear? Let me know in the chat. Can you hear me out there? All right. Hello, CZ Chan, Eloisa, Zhonghua. Hello. It's nice to see you again. So, in today's lecture, we're going to look at these fundamental theorems of calculus. But before I do that, just remember on Tuesday, the writing assignment is due, okay? And on Monday, I'm going to have a feedback session for the writing of the assignment, and that will be 12 noon Sydney time. So if you want to come along, I did ask students last time, are you interested in this? And pretty much everybody was interested in it. So if you want some feedback, come on Monday at noon, 12 o'clock, and we can talk about that. Come to my tutorial. All right, so let me go over here, and I will just share my screen with you. Okay, so Chrome tab, there we go. All right, so fundamental theorems of calculus today. So we sort of collectively call these FTC. All right, fundamental theorems of calculus. Now, fundamental means sort of basic and important. Okay, and you'll see how these theorems really make a difference to how we do integration and differentiation. It's a super important concept. Okay. All right. So we're going to look at two theorems. Okay, that's the subject of today's lecture. Now, the first fundamental theorem of calculus can be summarized in the following way. If you have an integral like this, where a is a constant and x is the variable, and you differentiate it, what happens is the integral and the derivative disappear, and you replace the t with a variable, okay, in this case x. All right, so that's the first one. Now, just note, in this notation, t is called a dummy variable. Okay, here, whatever letter you have here is not important, okay, because it doesn't appear in the final answer. So you could have S here or T or Q or something. You wouldn't want X there, okay? So X is already up here, so you don't want it down here, okay? So that's the first one. And the second one, which is probably what you're more familiar with. Oh yeah, f of a is no good either, Matt Apple. A is a constant, so here t is a variable. Okay. Because f of a is just a number, right? So when this is a function, okay, and when we differentiate a function, we know that all the constants disappear. Does that make sense, Madhav? Okay, so just bear with me. The second fundamental theorem of calculus is the following, right? If I am, say, integrating a function, yep, and I have an antiderivative, so that means the derivative of this capital F is equal to this. Okay, that's probably something that you're very familiar with, you know. This, not so much. Okay, so they're the two ideas that we're going to look at today. This is quite familiar. This is probably new. What this one says is, if you differentiate an integral, the things disappear and the variable just goes into the function. With this, it basically says when you integrate, you find an antiderivative or a primitive, and you look at the difference here. And it just involves the end points of the interval. Okay. All right. So this is where we're going. So important observations that we'll look at. Integration is the opposite of differentiation. Now, believe it or not, back when calculus was kind of first developed and played with in the 1600s, 1700s, people did not know that integration and differentiation were the opposites. Okay, so they studied them separately, and then eventually they were brought together. Okay, so knowing that they're opposites is really amazing, and we sort of take that information for granted today. So that's a really important thing. Wow. And the second thing is, if we want to calculate the area under a curve or any integral for that matter, then it depends only on the value of the primitive, right? So here we talk about capital F being a primitive of little f. Okay, so it only depends on these things. It doesn't depend on anything else. Now, you'll be pleased to know that in this lecture, we are moving away from Riemann sums to something more streamlined. Okay, Riemann sums are really like slow and they're not very nice to work with. Okay, so we're saying goodbye to the Riemann sums, and we're going to be using these ideas in this lecture. Okay, so the first fundamental theorem of calculus, the first FTC. All right. So before we state the theorem, let's just do some preliminary work. Suppose you've got two functions, little f and capital F, or lowercase f and uppercase f. We say capital F is a primitive or an antiderivative of little f if the derivative of big F is equal to little f. Okay, so for example, if I've got this function here, 3x squared, we would know that a primitive is x cubed because you differentiate this and you get this. Okay, so nothing too major there. But we can also choose, say, it could be something like x cubed plus 1. Because if we differentiate this function, we still get that. So primitives are not unique. There's more than one, and in fact, there's an infinite number, okay? But for our purposes, all we will need is one, okay? All right, so the process of calculating antiderivatives is like differentiating, but it's in reverse, okay? And the connection will be seen in the two fundamental theorems of calculus that we'll see. Okay, so the first fundamental theorem of calculus, the big intro. All right, So there's a few more assumptions here. We assume that we have a continuous function on this interval, little f, and we define another function by this thing here. So what have we got there? We've got the variable x in the top of the integral sign, and x is between 0 and a. So, you know, if I was sort of looking at this and this was my f, little f, and that's b, this might be a point x between a and b. And so when we're looking at the integral of this function on this subinterval, then it just would be the shaded area there. Okay. All right. So what happens with this? Well, if we integrate a continuous function, we get a continuous function from 0 to x, right? And this thing is differentiable. It's a differentiable function. And most importantly, for the examples we're going to see, the derivative of this is just f, right? So let me just write that a different way. If I'm differentiating an integral like this, what happens is the derivative and the integral disappear, and the dummy variable gets replaced with x. Okay, so this is probably a little easier to understand than this, but they're essentially saying the same things. Okay, well, so what? Well, the first fundamental theorem of calculus tells you that if you differentiate an integral like this, you get the cancellation. So the Riemann integral is the opposite of the derivative. So the process of integration can be managed just by using, you know, antiderivatives, which is great. We love that. Okay, we love that. Now, probably from an examination point of view, you'll be asked to compute these sorts of calculations for specific little f's. Okay, and it's not always easy. Even though this looks pretty easy, sometimes you'll get examples where it's not exactly looking like this. Okay, so that's my aim, to show you how you can use this theorem for various examples. Okay. All right, so I can do that just there. So this is the really important thing. All right. So here are two integrals that we want to differentiate. You can see in both integrals, the dummy variable is t, okay? So let's see. If I want to differentiate this, the fundamental theorem says, okay, well, I want a continuous function. That's always continuous. That's always continuous. And if I differentiate, I've got the same structure here. What I can do is cancel off. Okay, so the derivative and the integral cancel, and you replace t with x. Okay, now let's actually just confirm that we've got the right answer there. Okay, so you don't usually do this, but let's do it here. Okay, so integrate here, we'll get 1/3 t cubed. Okay, and I want to put in t equals x and t equals 1. Okay, I'll differentiate this in a minute. So it's going to be 1/3 x cubed minus 1. So the derivative what do you get? Well, the 1 disappears. This comes to the front. So you can see, hopefully, these two things are exactly the same. Okay. So here we did the integration first and then differentiated. Here we didn't even worry about the integration. We just differentiated and applied the first fundamental theorem of calculus. All right, now you get to a slightly more difficult one. There's no way of doing this example like we did down here. You cannot integrate this, it's too hard, and then differentiate. So we don't really have a choice for this one. But this is a continuous function, okay? The fundamental theorem of calculus says, well, these things disappear and you get this. So let's do it. So so this is going to disappear and the x will go in here. Okay, so nothing too difficult about the calculations for those ones. Okay, but you cannot do it this way. You cannot do the second one this way. You can't integrate first and then differentiate. It's just not possible. This is not a nice friendly function that's easy to integrate. Okay, so they're the sort of starter pack, the entry level ones for applying this first fundamental theorem of calculus. Okay, it says that if you differentiate an integral, then there's nice cancellation, and basically the integral is the opposite of the derivative. Okay, cool. Well, let's bump it up a bit. Let's change something in our question. And this is very common for the questions you'll see. Suddenly, you don't have the x here anymore in the upper limit of integration. You've got an x cubed and an x squared. So this requires a little bit of management. It's not too hard, but it does require a little bit of management. So what one strategy for these ones is to apply the chain rule. Okay. So when you don't have this nice, constant x in your integrals, the chain rule is usually a suitable place to start. Okay. So how do you do that? Well, remember the chain rule involves a substitution. Okay. So instead of x cubed there, I'm going to let u equal x cubed, right? So that's going to become u, and then I need a derivative. Okay, so with those two bits of information, what have we got? Okay, so d dx is just du dx times d du. That's the chain rule at work right there. Okay, I can replace x cubed with u, and when x is 0, u is also going to be 0, so that doesn't change. And the dummy variables don't change. So now I've got this nice form that is very similar to up here. I've got u's instead of x's. So I can apply the fundamental theorem of calculus to this. Woohoo! Yeah! Okay, so du dx is going to be 3x squared. This is going to be, well, replace t with u and get back to the original variable. Okay, so now it's just a matter of simplifying that. So it's going to be 3x to the power 8. Okay, so that's a little bit harder now because we've got one constant in the lower integral sign and then functions of x, not just plain old x. So the chain rule is a good place to start there. Okay, so for part B, let's have a look at that. It's very similar, just doing it for a little bit of repetition. So following on from this strategy, okay, by the chain rule, we'll get this, and going from here to here, actually, I'll make a note of that. From here to here is the first fundamental theorem of calculus. Okay, you probably should mention that. Okay. So, d dx. So again, when x equals 0, u equals 0. Okay. Okay, so now I'm going to do the chain rule. And now I can evaluate this by the fundamental theorem of calculus, and this is 2x. So that goes in there. And we want to get back to the original variable. So that's going to be sine x to the power 6. Da, 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 da. Yeah, so that is how you do those kind of problems when you've got a function of x in the integral sign. Now, probably the last difficult part is when you have functions of x in top and bottom. So that's our next port of call. Okay, that's what we're going to be doing next. Okay. So I might just pause there. What do people think of this method so far? Is it easy to follow? Do you have any questions? What is going on in your head? Let me know on the chat. Okay. Does it seem straightforward? Does it seem strange? Does it seem, super crazy? Just moving the camera around here. Quite satisfying. Let's go. It is nice to know. Is that me or is that the dog? That's the dog. The dog's asleep again. I'll put the dog to sleep. Sometimes calculus will do that to you, right? Okay. So, first fundamental theorem of calculus. Oh, come on, come back to me. First, oh, okay, web camera's gone a bit crazy. Go back to the other one. Too much dog. All right, so the first fundamental theorem of calculus basically involves differentiating integrals, okay? When it's nice and simple, these are the most straightforward ones. When you've got a function of x, you apply the chain rule. The third sort of level here is, well, what do you do when there's functions of x in both the integral signs? Okay, there's a question from Abdul Rahman. What if the function we put on top of the integral is not differentiable? Yeah, that's a good question. So we'll only really be dealing with nice friendly functions here, Abdul Rahman. So typically these are usually differentiable functions. Okay. Yeah. So I wouldn't worry about that. I've never seen one where these types of limits of integration are not differentiable, but it's a good question. Okay. All right, so let's move on to these kind of problems. Can anybody suggest what a strategy might be for these problems? Because these are the kinds of problems. There's no connection between t and x, Steve, because t is a dummy variable, right? So if I go back here, there's no connection between t and x, okay? Because this is just any variable. It's not related to x, okay? So you can replace t with anything you like. Yeah. So can anyone suggest what might we do here with a strategy to sort of break these things up into maybe more manageable things and then differentiate them? Can anyone suggest a strategy on how I might relate this all the way back to something like this? Any ideas? Yeah, that's an interesting idea, Aidan. You'll get a negative u down there. And what we would hope for is a constant down there, not a variable. So it's possible to make a substitution here, but it doesn't give us exactly what we want. Can anyone suggest what we might come up with? What a strategy might be for these kinds of problems where you've got something here and something here? Yeah, substitution again, Carl, but then you'll get something involving u down there. Use the old method is an interesting idea, although you can't integrate this. I'll give you an idea. What you can do is, oh yeah, that's not a bad idea too, Tom, but it's even simpler than that. What you can do, you can say, right, for any a between x squared plus 1 and negative x squared, I can break this integral into two parts. And then I can flip this integral. Yeah, a could be 0, right? Xuanhao, yes, a could be 0, for example. Okay, but it works for any a in here. Okay, so once you've got that, you can flip this and change the sign. Yeah, it's quite fun, isn't it? Okay, so you can flip this integral and change the sign. Okay, so let me give you an example here and we can work through it together. Okay, so for part A, right, we can go, right, we can say, so for any a between x squared plus 1 and negative x squared, you could choose 0 here. 0 is fine. Not a problem with that, like Xuanhao has suggested in the chat. Okay. And now what you can do is you can, for example, you can differentiate both of these integrals, right? So let me just move this one into the sort of a nicer form. Yep. Yes, Carl, you could make a equals 0, but it works for any a between here and here, right? You could make a equals 0. Yes, you could. Okay. You could make a equals 0. Okay, so now you can use the chain rule here and you can use the chain rule here, right? So let's make, I don't know. Okay, so let's follow your suggestions here. So we have something like, I don't know. So over here, we've got this. So this will work. Okay. All right, so we're using definite numbers now, which is great. And so now what we can do, we can use a substitution if we want to. You could let u equal negative x squared and u equal x squared plus 1 over here. But I mean, once you've done a few of these questions, you'll see it's actually very easy to do this, right? So let me look at this one. Okay, so you take the derivative of what's up here, bring it to the front, and replace t with negative x squared. Okay, so what's the derivative of this? Well, it'll be negative 2x. So that's the derivative here. And then you replace t with negative x squared. Okay, so what I've done there, in one step, I've used the chain rule and the fundamental theorem of calculus. The first fundamental theorem of calculus. Okay, the derivative of this comes to the front. This replaces x in here, and the integral and derivative sign disappear. Okay, same with this one. The derivative of this comes to the front. This whole thing gets replaces t. Da, 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 da. Okay, so now all you need to do is simplify this. Okay, so that's going to be x to the power 4, so 2x to the power 5. Okay, so that's a quick way of doing it. Same one for this one. Okay, for part B, I'll just do the quick way here. Right, so you break it up like we did here. You're going to get this thing. Oh, sorry, I want to differentiate that, don't I? Okay, this is going to be the same, except t squared is replaced with this. Mm-hmm. Okay, so when we apply the chain rule and the fundamental theorem of calculus, the derivative of this comes to the front, and this goes into here. So it's going to be negative x to the power 6. For this one, the derivative comes to the front, and this goes into here. Okay, so I've done those two quite fast, but once you've done a few of these using the chain rule, you should just be able to see it. Okay, so I don't think it's necessary to write out every step here when you're doing the calculations, because there's a pattern and you'll see it, right? You'll see it because the derivative comes out here, the integral sign disappears, you put that in for t. Okay. All right, so that's probably as hard as it'll get with these first fundamental theorem of calculus. Okay. But wait, I'm confused. What about the second fundamental theorem of calculus? Well, I'm glad you asked. Let's have a talk about that. Second fundamental theorem of calculus. Now, I kind of made a mistake here. You don't need this line. This is actually, you just remove this. This is actually from the first fundamental theorem. I just copy and pasted it over. But this is the important thing. Okay, if you have a continuous function and f is an antiderivative of f, that means this. Then this is how you can do a basic Riemann integral. Okay, so this all should be reasonably familiar. Okay, and like I said at the beginning, no more sums, no more Riemann sums, which is great. Okay, so I would hope that most people understand what's going on here with the antiderivatives, right? So, for example, if I wanted to integrate this, yeah, well, I know that an antiderivative of x to the power 4 is this, okay? And so this then is just 1/5 times 1 to the power 5 minus 0. Okay? So that's a really simple example of using the second fundamental theorem of calculus. Okay? So this is something that you should have worked with before, and hopefully it's very familiar to you. Okay? So where do you see this kind of second fundamental theorem of calculus? Well, you see it everywhere, and including when you're calculating area under a curve. Okay, so let me talk about a real simple example here, where we calculate area under a curve. Okay, so compute the area bounded by these curves here. Now, when I was doing this, you actually don't need this part to define the area, but I'll talk about that in a minute. Okay, so you can actually remove this. Okay, it's not necessary. Okay, so you've got a function or a curve, and then you've got these straight lines. Okay, so what the question is trying to ask you to do is to draw in these lines. Here's the vertical line, x equals 1. Draw in the curve y equals x squared, and draw in the curve y equals 0. So y equals 0 is just the axis here. And the area that they're asking you to compute here is this thing here. Okay? So it's very easy to compute the area, of course. So let's call this, I don't know, omega. It's just the integral from 0 to 1 of our function. Okay, and by the second fundamental theorem of calculus, we know we can find an antiderivative and then evaluate it at this point and this point. Okay, no more Riemann sums. Okay. All right, no more Riemann sums. Hooray! So we've got a few more minutes. Let me know what's happening in the chat, or I might just put my, hang on, I'll just change the session settings. So if people want to say something or ask a question about the lecture, feel free to do it. Now is the time. We have a few minutes. Yeah. So now is the time. If you want me to talk about anything, yes, Jovanka, sure. So here it is. It's quite a crowded slide. So is there anything you want me to repeat in that? It's basically you're applying the chain rule and the first fundamental theorem of calculus. Okay. So for this one, we don't actually have exactly what we want in the integral sign. We would prefer just an x in both of those. Well, we can make a substitution and come up with this. Okay. Yeah, that's fine. That's fine. Sometimes I go a bit fast. And of course, when I talk about maths, I tend to really get excited. And so sometimes I talk really fast. Oh, Abdul Rahman, I think the university is planning to come back in term one. So I expect that there will be some face-to-face classes in term one and some online classes in term one. I think they're going to try to do both. All right, let's have a look. So Abdulaziz, there's slide 8. So let me know if you have any questions. Yeah, Jovanka, the second fundamental theorem of calculus is the basic integration that you know from high school or from preliminary courses. Yeah, I hope everyone can come to Australia if you want to. You know, maybe I'll meet you in real life. Oh my goodness. Okay. All right, Ronan, let's look at your question. Where does 2x come from in the last part of B? Oh, yeah. So the 2x, so is this down, you're looking down here, Ronan? Let me know. Is that where you're looking? Okay. So we differentiate the function up here and bring it to the front. So it'll be negative 2x times a negative, which gives you positive 2x. Okay. So, in that example, I haven't written out all the, stuff here where you go through the whole chain rule and stuff. I've just gone, right, by the chain rule and the fundamental theorem of calculus, this goes to this and this. Okay, can you see here how this x squared plus 1 has become 2x? It's come to the front because the derivative of that is that. That's fine. That's fine. Yeah, face to face, Steve. Do you know what, Steve? Like when people meet on the internet, hang on, let me go back to my big head. Okay, Chen, I'll go back to your question in a second. When people meet on the internet, right? And then they meet in real life, there's a lot of research that says people actually they don't like meeting face to face. That actually sometimes people are a disappointment face to face. But everyone like I'm hoping that won't happen for us. But yeah, it's sort of interesting. It's like you have these ideas of who people are on the internet, and then when you meet them, they're like, oh, you're totally different. Anyway. All right, so Chen, yes. Please explain the chain rule and fundamental theorem of calculus again and how to apply both of them. So which slide are you looking at, Chen? Is there a particular slide you want me to talk about? I mean, this has got all the details, right? Yeah, so, okay, yep. So So here, right, in this one, in this integral, we've let u equal x squared. And in this integral, we've let u equal x squared plus 1. Okay? Sorry, negative x squared. Negative x squared. Okay? And then we've just applied the chain rule to both of those integrals, just like we did over here. Okay, so we made our substitution, we calculated the derivative, and then we applied the chain rule. Okay, so from here to here is the first fundamental theorem of calculus. Okay, so going from here to here is the chain rule, right? And then to actually do the derivative, we apply the first fundamental theorem of calculus. Okay, so just follow that. Use that substitution here. Use that substitution here, and then you'll get this. Okay. No worries. All right, is there any other questions? How's everyone going with the writing assignment? Is the writing assignment easy? Oh, is it Teachers' Day today, Hawk? Is it? Thank you. It is, it's Teachers' Day. Yay for teachers. Thank you, Hawk. It is, it's World Teachers' Day. Oh my goodness. Take a photo to, oh, hang on, I'll just put that up. Apparently it's World Teachers' Day. Oh, yeah. I don't look cool like those people, but anyway. Thank you for saying that. The black, Bailey, let's go back. Are you talking about page 8? Yeah, so are you talking about this to this? So, yeah, so you can think of this, if you want to integrate from 1 to 2, well, no, let's say 1 to 3, right? It's the same as integrating from 1 to 2 and then 2 to 3, right? Because if I've got the area under a curve, I can split it up and calculate that area and add it to that area. Okay? So it's the same principle here. Does it make sense, Bailey? Is there anything there that isn't clear? Yeah, so it's super easy. Yep. So as long as the 2 is between 1 and 3, to integrate from here to here, I can integrate from here to here and then here to here. Yeah, no worries. All right, everyone, I am going to stop the recording. Ai-Chen, hang around for a bit, and we can. I know you had a question for me, but everyone else, I will see you next week. And oh my goodness, let's see what's happening on Puppy Cam. Let's see if I can do this. Oh, looks like a cat. Let me see if I can change this over. Oh, yeah. And I'll see you on Monday. If anybody wants any feedback on their assignment, come in on Monday. Come into the 12 noon class. Okay? Thanks, everyone. Have a great weekend. Yeah, it's another one, Eloisa. Yes. So I'm going to do another one on Monday. Okay? So we will see you on Monday. Have a great weekend.